Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
Go above and beyond.
they become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast. I have Rajalingam Raja. He goes by Raj. He's the clinical professor. Raj, okay. He's the clinical professor of surgery, director of Immunogenetics and Transplantation Laboratory at UCSF, in San Francisco. And we're going to talk about his work. So, Raj, thanks for coming.
Thanks, Richard. It's a great pleasure to with. So, starting with what we are doing. So we are facilitating all the clinical transplantation occur at UCSF. Meaning, we need to do the tissue matching donor and recipient for any clinical transplantation. Kidney, heart, we take anything. We need to have a matching donor. You cannot literally put someone's kidney in someone's body to reject. Right. So that's what we are doing. So we do the genetic testing, serology testing, and we do all kind of battery of testing, and we select the best donor, reject the kidney immediately. We avoid that occurrence. Then we want to keep the kidney, or when I say kidney, it goes with other organs also. Right. So we want to keep the transplanted organ the maximum possible years, in 10 years. So that's what our main job. So we here facilitate almost 800 transplants. Wow. So UCSF is a big transplant program. So 5,000 people waiting for kidney transplant, which is like a 5% of the entire wait list.
That's a lot, yeah. What are the most difficult transplants to do, and why?
So I think the lung is the most difficult, and maybe heart, difficult transplant. Even the liver also. Surgically it is difficult transplant. But when it comes to the immunology, meaning how the recipient accept the organ, it's pretty much the same basic. There are some differences between organs because how the molecules are expressed between heart versus kidney, liver. But the basic principles are the same.
Have you ever done multiple organ transplants on someone at the same time?
It's a very frequent event, absolutely, yeah. So, a lot of patients who need a liver transplant, they also need kidney. Some patients lung or heart transplant, they need kidney. Some patients need both heart and lung transplant. So it's a lot of combinations, 2 organs or sometimes 3 organs.
What's the most transplanted case you've ever seen? Is there like a record?
What is that? Is a number of organs in same patients?
Yeah, in the same patient, yeah.
I think it's only 3. That depends on the center, yes. But some center does the entire internal organ transplant. They just take it out. It goes from chest to crazy.
What are some things that can't be transplanted? Can you transplant someone's colon or intestines? Not brain, I know, but what things can't be transplanted that would be nice to transplant?
You said it's the brain you cannot transplant, but there are a lot of research, so we did the publications with our collaborator at UCSF. You take brain cells from just newly born child. The child was born by dying, then you take that brain and extract the cells and infuse to the other children. There are 4 of them who had some genetic disorder, brain disorders. So it's not the whole brain transplantation, but the component or cellular component of brain transplantation. So people are doing it at USCF and other centers also. So then you can, by that way, you can cure some of the.
But are there any other, whole organs that would be nice to transplant but can't be? Can large intestines or small intestines be transplanted?
People trying all possible organs to transplant. People trying the colon and the small intestine is very difficult to transplant because of the immunology. The gut itself facing, so immunologically proactive organs is very hard to transplant. But people try to transplant everything. So like a hand transplant, they can transplant hand from one individual to another individual. They can do the face transplant. People lose their facial skin because of the burning. They transplant the face from another. They do the endometrium transplant. They transplant penis. So you name it, all organs they transplant.
Okay. So what kind of matching goes on? It sounds like blood type, and you said DNA work is involved. So how many different types of matching do you need? What are they?
In general is all this, the basic transplantation is the most of the scientific data we get it from kidney transplantation. Do a lot of transplant of testing. So all the knowledge comes from the kidney transplantation. So based on the kidney transplantation, we call them HLA, human leukocyte. So these proteins are capturing the viruses. Anything comes from outside our body that capture the HLA protein, capture those viruses or foreign materials, and give to our immune system to mount in reactions. So our body the immune system is protected against any invading pathogen. So these molecules called HLA molecules, and we have many of them. Each one has a different variety of molecules because the virus itself so rapidly mutating because it wants to cheat our immune system. So it changes its genetic composition to cheat our immune system. So to combat that, our HLA or our immune system, the HLA molecules also changing over the time. So that's what we end up in the population or individuals, everyone have their own HLA profile. So that becomes a difference. Each individual have their own HLA profile, so that we cannot find a compatible donor. Almost is not possible in a random donor pool finding a fully compatible HLA donor. But we try to match in some levels. We look at which is the critical gene that is important, that keep the organ longer. So it is called class 2 molecules, or particularly HLA-DR. So those are very important to match. So now we look more antigens, but generally it is HLA-A, B, and DR. So those three are important molecules to match between the donor recipient. But we have like 9 HLA loci. That means 18 antigens. So the more matching is better. If you match for all 18 antigens, that is great. But you cannot find that kind of donor in random donor in an unrelated pool. So you can get that kind of donor from within the family. Some siblings can be matched with the full HLA profile.
And I guess your overall goal is to reduce the amount of rejection and reduce the amount of immunosuppression needed once the transplant's done.
Absolutely, that's the goal. So the more matching is less immunosuppression or less problem. So that's the goal. But that's the goal. But it's not happening. When it comes to the unrelated kidney transplantation, the kidney comes from the deceased donor. So that goes to the people who needs the kidney, most sick people, or most people the most weighted on the wait list. It depends on that criteria. It's not working with okay, this patient is more matched with this particular kidney, so it's not depends on the HLA matching. Only a limited HLA matchings like the DR matching, but the organ allocation occurs based on who has been on the wait list for the longer, who is sicker, who are biologically critical patient. Those patients get the kidneys.
Okay, so immunosuppression, are there different levels of it, and when does it go wrong and why?
Majority of the immunosuppressions it depends on the transplant program. Immunosuppression, you don't want to over immunosuppress the patients because the patient will get infection because the immune system is the one protecting us from the infection. So you want to protect from the infection, but at the same time you want to keep the organ inside. The same immune system rejected. The immune system reject anything foreign materials, either from virus or bacteria or kidney from someone or the transplanted kidney. So the immunosuppression is such a critical aspect in transplant. You want to suppress good enough to keep the kidney in, but at the same time, you keep the immune system active against the invading pathogens. That's the tricky, but that's the active area of research. People identify what level of HLA matching needs to be done. So the big question is, can we grade or can we just come with a number, based on the molecular mismatches, can we gauge the level of immunosuppression. So that's the active.
Well, when does rejection happen typically, and what does it look like? What happens when you know someone's rejecting a transplant?
So the rejection can be two ways. One is the cellular rejection. So in the immune system, we have cellular component and the humoral component. Humoral is mediated by the antibodies. Cellular component is mediated by the T cells, B cells, other immune cells. To tackle cellular immunity is very easy. So we have a lot of drugs that was created from the autoimmune conditions or autoimmune board. So we can literally deplete a specific immune cells like a T cells, or you can suppress a specific immune cells like a T cells and B cells. So literally we have a variety of drugs available in the clinic, so you can suppress or deplete different cellular composition of the immune system. But on the humoral immunities, there is not much drugs. So the antibody-mediated rejection is very hard to control them. You need to remove the antibody by plasmapheresis, but it is not a permanent solution. So people can make, or the patient can make antibodies immediately within a couple of days. So the cellular immune response is manageable by available drug, but for the long run, the antibody-mediated rejection is a big issue. So after putting the kidney, the patients will develop de novo donor-specific antibodies against the kidney, which starts killing the organ. So that's the big.
Is anyone looking at the microbiome in regards to transplants? Of the organ itself, or of the donor and the recipient, because I would guess that, I don't know if the donor is given antibiotics before the surgery and then the recipient's given antibiotics before they receive the transplant. So maybe that's the best bet, or maybe it's better to not give antibiotics to the donor until after the organ's removed to preserve the microbiome of the organ. Is anyone looking at that?
This was is active research in 3-4 years back, and when microbiome was in place in immunology, it was very interesting aspect. So people, I think a couple of NIH-funded projects are looking at very systematically now, but overall there's not clear-cut correlations of how the biome can impact the long-term survival. But the big proposal is the biome can control or can modulate the immune system. It's it can generate T-regulatory T cells, so that can down-regulate the immune system so that the organ can stay longer. But we don't have any conclusive results on that. But again, it is an active field of research.
Well, what's the clinical protocol when you transplant an organ? Is the donor, again, given broad-spectrum antibiotics before the surgery, and is the recipient given the same, or how does that work?
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
So it's a if you take all the patients who needs the kidney, you can put them into different categories. One, very easygoing, meaning they never exposed to any HLA protein. So the matching we are talking about, they never exposed to any HLA, meaning by pregnancies, when they get the woman get the pregnancy, they are exposed to the husband HLA antigen, so that after a couple of pregnancies, they can make antibodies against the husband. Then the patient who already received a organ transplant, they can make antibodies against the organ. Then people get transfusions, they can make antibodies against the transfer protein. So if anyone not exposed to this transfusion, pregnancy, or transplantations, they never make any HLA antibodies. So we have like a 70% of the waitlist candidates for the kidney or that category. They don't make any antibodies because they never exposed to any HLA protein. So those are easygoing. You can put kidney from any individual. Then before you do the kidney surgery, just you take out the cellular immune compound, because there is no antibody immune compound, only the cellular compound. So using the depletion agents like anti-ATG or other kind of depleting agents, you can literally remove the cellular compounds. It's like a temporary, the cells will come back in. Then you put the kidney, then you give the patients everyday immunosuppressive drug, so then kidney can stay there. So then you balance based on the immune system but the other one is the patient who already exposed to the HLA because of the previous transplantation or pregnancy or several transfusions. So they make antibodies against many HLA proteins. So those are the candidates. We have 30% of the patients in the way. Those are the patients very tough to find the compatible. So that's our main job here in our lab. So we need to identify what type of HLA antibodies like it. If we then how much antibody they have it. So based on the antibody profile, then we are looking at who can be a very compatible donor. So that's our job. So,
what do they call the antibody profile? They call it, I mean, it's the HLA, but do they also call it like the immunosome? Is that a name that's ever used?
No, it's anti-HLA antibodies.
Okay, gotcha. So someone that's had to create antibodies to fight off a whole bunch of stuff, like you said, someone that's been pregnant, someone that's had multiple transfusions, et cetera, they're much harder because they have so many more defenses already in place. Absolutely. That a transplant is likely to reject from them more so.
That's absolutely, that's correct. Yep. So
okay.
Yeah, so that means there should be the HLA matching is very critical. Because if you do the mismatched kidney transplantation after 8 to 10 years, when the kidney is rejected, then when the patient needs a second kidney transplantation, the patient already made antibody, all this mismatch antigen. So less or more matching or less mismatch is very important. So that the patient can get another transplant. So this is very important fact in the pediatric transplant. One of the children who needs a transplantation within the earlier age, like 3 years, 2 years, or 5 years old. So they probably need at least 3 kidney transplantation in their entire lifespan. So in the beginning, we want to put almost a very highly matched kidney. Most of the time, the parents can be a donor because the parents are 50% HLA match. So we try to bring the kidney with the matched donor, so that the next transplantation will be easier. So that because the patient is not making.
Interesting. After a period of months or years, does the recipient get used to the transplant? Does it get easier or does it get harder over time?
No, it is easier. I think, when it's going to the dialysis center 3 times a week, that's a big interruption in their lifestyle, and staying on the machine for 4 hours to 6 hours, that's a tough one. So, and a lot of patients, and the patient on the dialysis time, their survival, the lifespan is much weaker. So they die. So it's like it's a lot of patients waiting for the kidney. They die because of the hardship of the dialysis. So once they receive the kidney, their life changes immediately. They become just normal. Not only the kidney, the heart, lung, they do themselves. So it's a big relief for patients getting a transplant.
So if rejection is going to happen, when does it typically happen? Immediately or a few weeks?
So, it's the good transplantation is everything is fine. So there is no antibodies, preformed HLA antibodies, all good, some level of matching. So the patient has to take immunosuppressive drug every single day just after the transplant. So as long as they take the drug every day, just every day for doctor advice, the kidney can stay like a 20 years, easy. But if someone doesn't take drugs, even missing for a week, it is very common in teenagers. They don't want to take the drug because they go 40 or other things. So they develop the antibodies against the kidney. So then they start rejecting, then they lose the kidney. If we cannot get into the correct time, they literally lose the kidney and they listed for the second transplant. So as long as they take the immunosuppressive drugs, they can keep the kidney. So the young patients, the the teenagers, and a lot of old people, because there's no care involved. So the old people missing suppressive drugs, then they end up with the kidney. And also, if there's some patients not having good insurance to cover immunosuppression, some government programs, now that I think they are going to change, the government is going to change, but if the insurance is not paying for immunosuppression after 3 years, I think, they start losing the kidney. But if they...
so even if I've had a kidney for like 3 years, I'm still likely to reject it if I stop taking my immunosuppression.
Oh yeah, so one can lose the kidney if they stop the immunosuppression even for a couple of weeks. Even 1 week is good enough. They can start losing.
Even if I've had it for years.
So if you take the immunosuppressive drugs, you can keep the kidney for up to 20 years, solid 10 years, 10 to. So the immunosuppressive drugs are key. You don't want to miss that drug.
Yeah, there was a movie, Blade Runner, I guess, where they would repossess, transplants that people didn't do what they were supposed to do. But thank God that doesn't happen, if somebody doesn't pay their bill, for instance.
That's correct. So now it's the new bill called Immuno Bill, so that allow patient to buy the insurance company to pay for the immunosuppressant for longer period, not just.
Oh, I didn't realize that. So insurance companies would only pay for 3 years, let's say?
3 years, I think sometimes 2 years. Then, if the patient doesn't have money to buy the immunosuppressive drug, that's quite expensive, I guess. And, that's a problem.
That's horrible.
Yeah, that is.
I didn't even know that. I was just kidding, but.
So it's going to change. That's a good thing.
Yeah. So what's new that's being worked on in terms of transplantation? Less immunosuppression, but still maintaining the organ. Where's the advances going to come from, you think?
So the advances are more matching, if what kind of matching will enhance the life of kidney transplanted organ. So we are working on to identify what are the relevant mismatches at the nucleotide or the amino acid more granular, not just looking at the antigen. So that's the one thing going on. So hopefully we'll identify which mismatches are bad mismatches or which mismatches are acceptable mismatches. So that's the one active projects we and many other. So the other second active research, we have hundreds and thousands of HLA antibodies. We want to know which one is clinically important, which one is so detrimental on the graft, which one is not relevant to the curl. So that's again a big chunk of work that we are very actively in, because some patients patients are not transplant candidate because of so much HLA antibodies loaded in their bodies, because they are second transplant or third transplant candidates, or because of their unique HLA types. They are making a lot of antibodies. We want to identify which antibodies are very irrelevant, not rejecting them. So that's a big active research. Then in outside our labs, so there are a lot of labs doing tolerance. The same immune cells, the T cells, a subset of them, majority of the T cells reject the organ, but a subset of T cells can suppress the T cells, or that means it can enhance the organ outcome. So it can suppress that. It's called T regulatory cells. So people trying to take the cells from the recipient and make the T regulatory cells outside in the labs, then put it back to the recipient. So that's another line of research going on. So if that works out, that's going to be great. So you don't need to take a lot of suppression. So only just the immune system, the recipient immune can do. So that comes with a lot of challenges. It's not easy. So that's one way. So then there are a couple of big centers involved in just transplanting the bone marrow. You can introduce the new immune system from the donor before you put the kidney in. So basically you take the recipient and you remove the recipient immune systems, or at least some level. You deplete some of the immune system from then you put immune cells from the donor. Is called bone marrow transplantation. Then after 6 months, you put the kidney from the donor. So it's kind of chimera. So you already prime the recipient and body to receive the kidney transplant. So that's another activity. So so that's all good stuff going. It's all challenging things.
How well does the preparing the immune system with the bone marrow transplant first work?
It's I mean, some center climbs is doing great. It all depends on the patients. Again, it goes back to how much HLA match between these individuals. So these are the very limited studies, only 10-15 patients they studied. So it's we need to learn a lot. But this is a great approach. So when the deceased donor, if it works out, you can do the bone marrow transplant and the kidney from the same donor, from the deceased donor. So it's all the novel ideas, but so we need to wait for the solid. So
I don't know if this is an ignorant question, but the HLAs, so these are antigens that exist only on leukocytes, or are they on all the cell types of the transplantable organ?
It exists in every single cell that we have. It's kind of, the name is like a misleading. It's called human leukocyte antigen. But when they invented this HLA, before that, so it's only one antigen. That's the red cell antigen. So then people call it, okay, it's a white cell antigen. So that's what the naming started. But over the time, HLA is there every single cell. So if there is no HLA, that cells will be susceptible to infection because it cannot present the antigen.
So over time, everyone becomes more and more unique and more defensive of their particular arrangement of cells and everything else.
So that's the idea. So there's a lot of research already published. So if the people having various HLA types, so one can have 18 different HLA molecules. Those are the classical class one that can be expressed and used for the protection. So the 18 HLAs we have, but if some loci can be homozygous, that means people can have only 9 HLA because of the homozygosity. So there will be a spectrum. People can have only 9 HLA versus 18 different HLAs. There's a spectrum. Some people can 10 and some have 11. So because HLA present viral peptides or the pathogenic peptides protect ourselves from the infection, so having more HLA is a greater advantage for the people who can defend against a variety of pathogenic peptides compared to the people who has only 9 HLA molecules. So having more diversity in HLA people have it, they are very tolerant or more protected against. So that has been published in many. It is called heterozygous advantage.
So throughout your life, though, your HLA profile changes a lot, or is it stay pretty similar to other people in your family?
It never changes. It is predominantly expressed. So whatever you inherited from the parents, you expressed. So it never changes.
Oh, I thought that you said people that are subject to insult throughout their life, they're harder to receive transplants. That they've had more infections and things like that. But is that not HLA changing?
No. So this the HLA never changes. HLA in our body never changes. But if you are exposed to someone's HLA because of transplantation, pregnancy, or transfusion, then you develop antibodies against the third party HLA model. So it is an anti-HLA antibody.
Okay.
So then you cannot bring an organ that is so against the antibodies. So you need to
does anything change the HLA profile? Can you deliberately provoke it to change and update itself?
So that's the CRISPR technology comes in. So people trying to do that. So the Xenotransplantation has been there in the field for many years. So the big problem is you get the organ from the pig and you transplant them, but the problem is that the pig doesn't comes with the same molecules like HLA molecules that we are talking. So that is HLA is very critical to present antigen. So now they are using the CRISPR. They are trying to engineer the pig expressing human HLA so that they can the transplantation between pig and so that's again another active. So that's the CRISPR technology is helping.
Has anyone? I don't know. This is probably a long road, but has anyone tried to look at like the extracellular vesicles given off by a given organ, before it's transplanted and then after it's transplanted, to compare them to see if there's any indicators of change?
Yeah, so that's again, it's a long-term research. People are trying to do this, so when the organ is harvested and they need to store it until it goes to OR of the risk. So now a lot of organs fly from anywhere from one corner of the country to the corner. So the kidney flies, liver, heart, lung, all organs can fly any place, one place to another. So during the travel, they keep it in a solution. It's a cold solution. So that solution, they had this reagent to preservative. So that helps the vesicles can go into the cells to preserve the decaying, or slowing down the decay, or even it can down-regulate the expression of HLA molecules. It pulls the HLA molecules, or it's not expressed more HLA molecules. So again, those are the active research going on. You're absolutely correct.
Well, it's very complicated, but so all right, Raj, what do you think will be the near-term wins or advances in understanding? What do you think in the next maybe 5 years that we'll see that's different about transplantation?
Oh, there are a few things. One, people are developing the mechanical organs for the kidney. They implantable organs. They make a mechanical kidney. You can implant them. That stays like you don't need to charge anything. Just it works like any other implanted the ventricular device type. So that's like implantable organs people are working. I think that has a lot of potential. There's a UCSF group working on that. So a lot of investors have pouring money. So a lot of industries are working on that kind of projects. Then the second is I think with the CRISPR technologies, the xenotransplantation is very active now. So they are knocking down a lot of even molecules from the pig and see one can tolerate, the recipient can tolerate the pig organs. Xenotransplantation, another big lot of hope for the transplant. So I think with these two, it's going to be great. So the other one is the synthetic organs. You take the organ from unusable organs, just remove the cells, and you bring the cells from the recipient, and you modify the organ, or you generate the new organ from the materials from the recipient. So you just grow the organ in the petri. So that's again so another active. So I think all these three is going to benefit if one or other works out.
Yeah, definitely.
Yeah.
Well, Raj, what's the best way for people to find out more about your work?
So we have this website, UCSF HLA lab. So you can find us. So you can find us from our publication. So HLA transplantations will be there.
Okay. Oh, last question. Is there any incentive to? I don't know if it's hard to do, but can you have your HLA profiled? You know, if you wanted to set up a network of people that say not only, hey, I'm willing to be an organ donor when I die, but I'll get the testing done. So here's my HLA profile so that, it's faster to find recipients. Would there be any use for a network like that of info?
So it is already there for the bone marrow transplantation. The donation is only the bone marrow or the little bit blood from the just peripheral blood. So it's not even bone marrow nowadays. You can collect only the stem cell from the peripheral blood, and you can save the patient. So that's we have like a 5 million volunteer donors in US. So they want to give the blood cells for blood stem cell. For the kidney, there is a registry. People wants to donate one kidney. There's called National Kidney Registry. There are a couple of other things. People can register. I think you can find them in the Google. If someone wants to donate the kidney, they can register and give the kidney. I think only those things. So liver. There are some living transplantation, living donation, but most of them are related. But the liver donation is a piece of liver one can do. But the heart and lung so that's only the cadaveric or the deceased also.
All right, Raj. Well, very good. Thanks for coming on the podcast, and I appreciate it.
Thanks, Richard. Thank you very much.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.